All right, let's jump right in. We're going to talk about something, well, it's a pretty revolutionary idea. What if, instead of just drowning in AI and data, we could actually teach it the rules of the universe, the laws of nature themselves?
And that brings us to this really fascinating question. We're all used to hearing that AI needs these giant, massive data sets to work its magic. But what if it didn't? What if there's a way to use AI to tackle some of science's biggest, hairiest problems with almost no data at all?
So, to really get why this is such a game changer, we've got to first understand a major hurdle for AI. It's what people call the small data problem.
Okay, so here's the core issue, right? When you're training an AI to recognize cats, you can throw millions of cat photos at it. The data is cheap and plentiful. But what about science? Think about trying to model the inside of a fusion reactor or predict a hurricane's path. You can't just get millions of data points. It's incredibly expensive, sometimes physically impossible. This is what's known as the small data world. And honestly, it's where most traditional AI just falls flat.
I love this analogy because it just clicks. Imagine a standard AI is like a student trying to learn French by just memorizing a million French sentences. Yeah, they might be able to repeat a few things, but they don't actually understand the language. They don't know the grammar. Now, a physics-informed AI, that's like giving the student the grammar book. It's not just memorizing, it's learning the underlying rules, and that makes all the difference. Okay, so how on earth do you actually do that? How do you teach a bunch of code about physics? Let's get into the nitty-gritty. All right, the official name for this is a physics-informed neural network, or PIN for short. And you can think of it as a hybrid. It's got two jobs. Job number one, match the few real-world data points you give it. Job number two, and this is the crucial part, it has to make sure its predictions obey the laws of physics. These laws are often written down as things called partial differential equations. And yeah, I know that sounds super intimidating, but don't worry about the name. Just think of them as the universe's official rulebook. They describe everything from how heat flows to how waves move. So what's the secret sauce here? How does it actually learn? Well, it all comes down to how it's judged during its training. Its score, or what engineers call its loss, is made up of two parts. First, how far off is it from the real data we have? And second, how badly is it breaking the laws of physics? The total error is just those two things added together. The whole training process is really this elegant balancing act. First, the AI makes a guess. Then, and this is the clever part, it uses some built-in calculus to figure out exactly how much its guess violates the physics rulebook. Finally, its internal machinery gets to work, tweaking and adjusting its own wiring to try and make both of those errors, the data error and the physics error, as small as possible at the same time. Okay, that's the theory. But what can you do with this stuff? Well, for starters, you can solve the unseen. You can take just a tiny, tiny sliver of data and use it to predict how a whole complex system is going to behave. To give you a sense of just how wild this is, let's look at a concrete example from the research. They tackled the Schrödinger equation, the famous one from quantum mechanics. And to do it, they gave the AI just 50 data points. That's it, 50, to describe an entire quantum wave function. And the results? Frankly, it's mind-blowing. From just those 50 little breadcrumbs of data, the PIN was able to map out the entire complex behavior of the wave over all of space and all of time. It literally filled in all the missing pieces just by using the grammar of quantum mechanics as its guide. The researchers who did this work said it best themselves, and they had the numbers to prove it. The final error was tiny, something like 1.97 times 10 to the minus 3. For anyone who's not a math whiz, that basically means it was incredibly, incredibly accurate, especially when you remember it started with almost nothing. Okay, so solving equations with sparse data is amazing. But what if we could take it a step further? What if the AI could not just solve the equations, but actually discover them? This is where it gets really interesting. So, for their next trick, the researchers pointed this thing at fluid dynamics, specifically the super complex Navier-Stokes equations. The challenge was this. They gave the AI some scattered measurements of a fluid's velocity, and that's it. And then they asked it, okay, based on this, can you work backward and tell us the fundamental properties of this fluid? It's literally like being a detective, trying to solve a case with just a handful of clues. And check this out. The results are just stunning. This table here shows the true physical parameters of the fluid, these lambda-1 and lambda-2 values, compared to what the PIN figured out. The error is basically negligible. And get this, even when they intentionally messed up the data by adding 1% noise, the AI still nailed it. It saw right through the noise and found the underlying truth. But here is the absolute jaw-dropper from this experiment. The pin was able to map out the entire pressure field of the fluid. And why is that so incredible? Because the researchers never, not once, gave it any data about pressure. Zero. It figured it all out on its own, simply because it understood the physical law that connects velocity to pressure. This isn't just pattern matching anymore. This is starting to look a lot like genuine understanding.
So this is all amazing stuff. But where is it all headed? What's the next frontier for this tech?
Now, the people behind this are the first to say that this is still a new field. There are a ton of open questions they're still working on. Things like how big or small should these networks be? What's the absolute bare minimum of data you can get away with? Is there a better way to measure the physics error? Answering these is what's going to push this technology to the next level. And all this really leaves us with one big, exciting question to ponder. We've just seen an AI that can learn the known laws of physics. So what happens when we point this kind of tool at problems where we don't know the rules? What hidden patterns, what undiscovered laws are waiting out there in the world, not just in physics, but in biology, in finance, in climate science, that an AI like this could be the first to find?